So for those of you who haven't heard of Arduino, what is it? Well, it really is a collection of things. And I think ecosystem probably describes Arduino the best. They do make hardware and sell hardware kits. So the kits can include things like resistors and LEDs and diodes and things to make general projects. They also sell microcontrollers. So here's an example of probably the most popular version of an Arduino microcontroller, the Arduino Uno R4. They also produce what are called shields. Those are things that sit on top of these headers and provide extra utilities, things like a Wi-Fi shield or a motor driver shield. And that leads to the next part here, the open source software, the libraries. They try to make it as easy as possible to produce electronic gadgets with the least amount of resistance that they think is possible. Compared to 15 years ago, if you wanted to create something that automatically switched your light switch on and off every 15 minutes, it's a lot easier to do that with an Arduino than it would have been 15 years ago doing this all from scratch without all the libraries and documentation that they have for their hardware. I think one of the biggest innovations, though, is the design of their bootloader, which means that you can update the programs on your microcontroller without having a hardware programmer. It's hard to stress just how much more complicated this can be without the bootloader. Every time you wanted to change the program on your microcontroller, you'd have to connect multiple wires, not just a USB connection, and use a special piece of software and a special piece of hardware to flash the ROM on your chip. So that's really what Arduino is providing, is this ecosystem of hardware and software and tutorials and support. So given that, let's look at what this blinking sketch would look like in Arduino. We have our setup code, and we have our loop code. Compared to JAG, this would be just anything outside of main. But unlike an interpreted or bytecode language like Toit or Python, most of your code needs to reside inside of a function that can then be called and jumped to, instead of just running when the program starts, or rather when the bootloader jumps into the application section. So you can see in the setup here, we set the LED's output. We set the LED's pin to be in output mode. And in the loop, we set it high to turn it on, delay 1 second, so it's on for 1 second, set it low, delay 1 second, so on for 1 second, off for 1 second. Comparing this code to what we saw a few slides earlier, that is what they're trying to do, is basically shrink this down into this. They also have standard names for things, so you can pick up an ESP32 or an AVR, one of their line of microcontrollers, and if you're using Arduino, you can just say all caps LED built-in, and if that board, that particular board, whoever it's developed by, if it has a built-in LED, that pin number will be assigned to LED built-in. That's part of this ecosystem. So the manufacturer, I think it's 3E, Seed Studio, that made our ESP32, the version of ESP32 that we're using, they created a library that does things like set LED built-in to the correct pin value. This means you can run this exact same sketch, which is what the Arduino ecosystem calls them, sketches. You can run this exact same sketch on thousands of different boards without having to know exactly what pin the LED is connected to. So that's your preview of Arduino code. Let's talk a little bit about what makes the Arduino bootloader special. Really, the part that makes it the most special is programming over serial. So as I mentioned before, instead of having to have a hardware programmer, we can have our microcontroller with a USB connector on it and plug that into our laptops. have our code in here and program our microcontroller, just as easy as that. So what the bootloader is responsible for, and the code that Arduino is running behind the scenes, is it's constantly looking for data on this serial connection. And I call it a serial connection. There's really an extra chip on here that's converting the USB data into a serial format. And by format, I really mean converting the USB wires into the wired connection needed for a serial interface. And so back to our picture of memory, you have your application existing somewhere in there, and Arduino has its code running in here, and the original bootloader is running on here, or only running at startup, but still existing in memory. The Arduino code is then able to override yours with a new version of the app whenever you send or hit the upload button in the Arduino IDE. And it does that by essentially not just running your code at all times. The reason any sketch will look like this with a setup function and a loop function is because there's extra code running outside of those two functions. So this is more or less what an Arduino main function looks like. It calls init to initialize a bunch of things behind the scenes in Arduino, init variant, which are variant-specific initializations. So for example, the ESP32 will have different initializations than the Arduino Uno. And then it calls your setup code. And then in a loop, it calls your loop code. So jumps over and calls your loop code. And then checks for serial data. And if there is serial data, it might do something like override your application memory. This does mean we have some limitations on what code we can put in here. Inside your loop code, you might make the mistake of having something like while true, and then running some code that always runs. And if the loop function never exits, you'll essentially lose the ability to program over it. You'll get stuck in that loop, and the Arduino code will never be able to run and overwrite what your code is, the code you already have uploaded. This is a pretty stripped back version. For those that are curious, I really recommend looking at these two links here. The code I have is really just from this first link, which is the AVR version of the initialization code. If you want to look at the more complex version for the ESP32, which has a lot more functionality, I would take a look at that second link. So given these limitations, I have a couple of key parts, key pointers that I want you to remember when you're writing embedded software. Don't block other tasks with delays. The more delay code you write, the worse off your entire system will be. You need to deal with hardware and time constraints in another way. In fact, the way that we'll be using is called an event-driven approach, where we're going to be using finite state machines, or FSMs. That sounds fancy, but it really is just a way to structure your code that I'll show here shortly. Here is here's a really strong example of why you shouldn't write your code this way. This is the same blink example from above. The setup function is fine. All we're doing is calling a single function. But inside here, we're calling our functions, and it's really these delays where things aren't happening the way we might want them to happen. The delay functions won't cause Arduino that much problem. The Arduino system can do things during the delays. However, if you look at what we have on the right-hand side over here, let's say that we're also setting up motors in the setup function. And then inside the loop, we want to check to see if the motors should halt or not. I'll ask you to pause the video here, but looking at the rest of this code, what's the worst case scenario for how long the motors will continue running before halting? Hopefully you've taken a chance to pause the video and answer that question, but it's much longer than I would feel comfortable with. Worst case scenario, we hit both of these delays. So let's say we need to let's say we run this line of code here, which checks to see if the motor should halt, and let's say it shouldn't, but then immediately after we run that function, we receive a signal that says the motors should halt. Well, they won't halt until after this delay, and then after this delay, so it would be 2 seconds. A 2-second delay before halting the motors. A lot can happen in those 2 seconds. So let me show you an example of blinking without blocking. So this version doesn't have any of the motor code in it yet. I just wanted to give you the simplified version of blinking without blocking. Here's the original version. And you can see all we really need to do here is only run these digital write commands. Whenever we detect that enough time has passed. So instead of manually calling delay, we'll just say if not enough time has passed, we'll come up to the top. And we keep looping extremely fast because all we're doing is checking this single condition. Running this one function and checking this single condition. So we're not really blocking. So what does that mean if we introduce our motor setup again? Well, this LED blinking, again, only takes as much time as when the if statement is true, having to turn on an LED. If the if statement is false, we just immediately jump down. So the worst case scenario for here is however long it takes to run this set of instructions. So a handful of instructions. So this will make your code much more responsive if you write in this manner. Taking this a slightly step further, your code should more or less look like this. You're going to initialize some global state for different modules. Maybe we have a LiDAR module and a motor module and another one for the compass. Each of those will need to update at different rates. We'll want to update our motors at least 10 times a second, but maybe the LiDAR we only need to update every 2 seconds. Inside setup, we initialize non-trivial global states. So setting something like blink interval to 1000 we can just initialize in the global scope. But setting a pin mode is going to require several instructions to run, and it's not just setting data in memory. So that's what I mean by non-trivial. Anytime code needs to run. And then inside your loop, you're going to have these really short updates or polling for your different modules. So we'll end this set of videos by just showing how these different pieces map to what I've shown so far. We have our global state. We have our update periods. We have our non-trivial global states to initialize. And we have our short updates and polling for the different modules.